Good morning, everybody. Welcome to again one more lecture in fluid mechanics. Today's discussion will be on one of the important properties of fluid, which is called viscosity. Viscosity has very large significance in the study of fluid mechanics. What is this viscosity? How can we know the fluid is possessing viscosity? Before I take up an activity to make you to understand what is viscosity, first let me just start with what is the definition of viscosity. Viscosity is the resistance to the movement, resistance to the flow. It is the viscosity is the internal friction between the fluid particles. It is the resistance offered to the movement of one fluid layer above the other. It is the inherent property of the fluid by virtue of which it offers resistance to motion, resistance to the movement of fluid layers. Then, what is the activity through which we demonstrate the viscosity? Just look at the four jars which you are seeing before you. In that jars, we have filled the first one with some oil, the second one, in that four jars, we have filled the first one with water, the second one with some oil, third one with some syrup, fourth one with honey. I have taken a marble stone and put it in the first jar, the water. Again, another marble I put in the second jar, an oil. Third one, I put another marble in third jar having syrup. The fourth marble I kept in the fourth jar where honey is available. Now, if you observe the motion of that marble in the fluid, marble is same. In the first one jar, it reaches quickly to the bottom. Second, a little bit slower compared to the first one. Third one, again it is a little bit slower compared to 1 and 2. The fourth one, it is very, very, very slow. Liquids are same. I did not do anything. But if I observe the motion of the marble, In all the four jars, we observed a phenomenon, a different speeds for the same marble. That means there is an inherent property for the fluid which is offering resistance to the motion. The first one, mm, resistance is less. Second one, a little bit more than first one. Third, a little bit more than second. But the final one, resistance is more. What is this resistance? And that resistance is precisely the viscosity of fluid. That another example also I can quote you. Take just an inclined plane. On an inclined plane, just pour water first. Observe the speed at which it is moving. Okay. Same inclined plane you keep aside and pour it on it honey or castor oil and observe it. It flows very slowly. Same inclined plane, but one here the fluid is flowing faster, there the fluid is flowing very slow. What it means in the there is a resistance to the fluid flow, which is inherently not permitting it. That internal resistance is the viscosity of the fluid. With this introduction, let us straight away move to the whiteboard to understand what are the various topics in this viscosity. So, in today's class, we discuss more on viscosity. Just now, you have seen the activity. Now, I will take into the order. First one is definition. Then second one is the activity, which I have finished already. Third one is causes of viscosity. Fourth one is Newton's law of viscosity. Fifth one is the explanation and derivation. Then sixth one is what are the units of viscosity. And seventh one is kinematic viscosity. Kinematic viscosity and its units. So these are the various topics that which we will discuss in today's class. So after seeing the activity, I will now concentrate on what is the definition of viscosity. What is the definition? It is the property of the fluid because that is what we are talking about. It is the property of fluid. First thing that should come to your mind. It is the property of fluid. What it is the resistance. This is the second word. It is the resistance offered to the motion or movement. It is defined as that property of fluid by virtue of which it offers resistance to the movement of one layer of fluid above the other. Just I will, for better understanding sake, you take a fixed plate. Just understand it. Now, this is another plate which we have really dragged with a force F. This entire space between these two plates we have filled with a fluid. Now, this fluid can be considered as layers of fluid. Many layers. Like this, you can call the entire fluid which is filled in this space can be considered as so many layers of fluid. As this plate is fixed plate, the particles which are adhering to this plate will have the velocity of this plate. As it is a fixed plate, naturally its velocity is zero. So all the fluid particles adjacent to it will have a velocity, fluid velocity as zero. So this is called no slip condition. What is no slip condition? At the boundary, where the boundary is a fixed thing, where the velocity of fluid is zero, there the fluid which is adhering to that will have the same velocity as that of the boundary. So therefore, that velocity is what we call it as the zero velocity, which is called as no slip condition. Whereas the next layers will not have zero velocity. It will have the velocity because already this top plate is now dragged with a force of F. So naturally, the particles which are adhering to it will be moving with some velocity V, right? So what will happen? The velocity is changing from zero at the fixed plate to V at the basically the moving plate. So that means the layers will have different velocities ranging from zero to V. That is what we should understand. So when it is changing from zero to V, actually, so the velocity distribution will be like this. Assuming the distance between the two plates is very small, we can consider it as linear. See how here the velocity is zero. Slowly the velocity is increasing, and at this place the velocity is becoming basically the velocity of the plate, which is equal to V. So this is first you should understand. My question is why here the velocity is zero and why basically as the layers it is increasing. This is due to why this is all occurring is basically fundamentally due to the resistance offered. That means This fluid layer, which is having a zero velocity, offers resistance to the next adjacent fluid layer. This next adjacent fluid layer again offers like that. So this resistance effect is nullified over a till basically it is being applied with some force, some velocity. So that is why this resistance is mainly due to the viscosity of the fluid. So now coming to what are the causes of viscosity? The causes of viscosity are two reasons. The number one is the cause is cohesion. Number two cause is basically the molecular momentum transfer. So what is the cohesion? Cohesion is nothing but the attraction between the molecules of the same fluid. Cohesion in water means the attraction between the molecules of water molecules. Cohesion in mercury means the attraction between the molecules of mercury. Then what is molecular momentum transfer? What is this molecular momentum transfer is? Normally, we all know that actually the molecules will be continuously moving inside the basically the substance due to the continuous movement of molecules. Due to the continuous movement of molecules, right? Due to the continuous movement of molecules, collisions occur. When collisions occur, momentum transfer takes place. Because of this momentum transfer taking place, resistance is offered. Because of cohesion, resistance is offered. In case of liquids, if you take it, in case of liquids, if you take it, cohesion will be the significant factor for viscosity. That's why mainly in case of liquids, we say that the viscosity is due to cohesion. Here, the molecular momentum transfer is negligible. Coming to gases, here mainly because of less molecules inside a gas, the continuous agitation of these molecules increases the collisions actually. In gases, actually, the collisions are more. Hence, momentum transfer is significant, but cohesion is negligible. So why viscosity is there for basically the gases is mainly due to the molecular momentum transfer, whereas in liquids it is mainly due to basically this cohesion. So that next, let us go What is Newton's law of viscosity? So, Newton's law of viscosity basically it states that the shear stress is proportional to the rate of angular deformation. In other words, the shear stress is proportional to the velocity gradient. Shear stress is represented by tau is proportional to what you call it as rate of angular deformation is nothing but dou theta by dou t. Shear stress is proportional to dou v by dou y. This is called velocity gradient. So this is a rate of angular deformation and this is velocity gradient. And this is commonly we use it in now in any of the things in future. So therefore tau is equal to mu into that dou v by dou y, and some we will write it as tau is equal to mu into dv by dy. So where this constant of proportionality, the constant of proportionality is called viscosity, or more precisely dynamic viscosity. Now, next question is you people will ask me straight away, sir, how dou theta by dou t is equal to dou v by dou y? No issues, but this is not related to the context, but only for academic understanding sake, I will tell you how basically this dou theta by dou t, how dou theta by dou t is equal to dou v by dou y, that we will see it, that is rate of angular deformation. This is only just interest for you, not any exam point. Rate of angular deformation is equal to velocity gradient. Suppose I take the space between two parallel plates I have taken. One is fixed plate I have taken, and this plate is dragged with a force F. So it is moving with a velocity V because of the force. Kindly remember, because of the force. So that is what is happening. So now if I take it, what is happening? Suppose now initially this is the thing. So the velocity here is 0, here also 0. Now what we have done, this upper plate is dragged with a force F. So because of that force F, naturally a velocity V as we have noticed.
So when once we have noticed the velocity of v in this, how it changes, for example. So how it changes if I take it, for example, now if you see how the velocity diagram changes, this is how the velocity changes actually. So when the velocity changes like this, if I take it, this angle is theta. This is what we call it as, this theta is angular deformation. What is this theta? It is angular deformation, right? What is the rate of angular deformation? Rate means what? Rate means per second. So rate of angular deformation is equal to, normally we need to do it per unit time. So that is represented in differential form. It is dou theta by dou t. So this normally what we can write, this d theta is equal or dou theta by dou t or d theta by dt. So in normal terms, what we can write, dou theta is dou theta is equal to, generally we write dou theta is equal to, what is dou theta? Basically, if you take it, it is nothing but, because this plate distance between the two plates is very small, dou theta also can be written as theta, and theta can be written as tan theta. So if I write dou theta is equal to tan theta, then it is nothing but actually it is opposite side by hypotenuse. Sorry, opposite side by the adjacent side. That is what we mean by tan theta, right? So my question is, so now if I take it, tan theta is equal to, if I take it in a small, if this plate is moving with a velocity v in a small, basically this is the distance, basically if we, I write it as a very small distance, very small distance dy. So naturally this plate will move with how much velocity actually, if I take it with how much velocity it is moving, if I take it, so naturally if it is moving with a velocity of dv, for example, right? If the v is the total velocity of the plate in a distance of dy, it is moving only a basically dv into, basically what I can write, what the distance I want, because dv is the velocity. So how much distance it moves? It moves only a distance of dt. D velocity into time is equal to distance. So how much it moves? dv into dt. So what is tan theta? It is dv into dt divided by dy. So if I write what is dou theta by dou t, then it is nothing but dv by dy. So that is why the rate of angular deformation is equal to, it is nothing but actually we can write it as a, we can write it as basically the velocity gradient, right? This is the point. So after this, we will go for Newton, the next lecture actually, our next topic we will go. So this part is only to understand how rate of angular deformation is equivalent to dv by dy. Here I wish to tell you something actually. Normally, if you are reading the solid mechanics, in terms of solids, you also know that this shear stress tau is equal. Shear means horizontal force. So that shear stress tau is proportional to angular deformation. Directly, tau is proportional to theta, and the constant of proportionality tau is equal to g into theta. That g is called modulus of rigidity. That is what you must have studied in solid mechanics. Now in fluid, what is the problem is that theta is not constant actually. In the case of solids, when once the shear stress is applied, the rate of the angular deformation is fixed, some theta, that's all. Beyond that, if you want to apply also, it fails, but it will not change. So that theta is not dependent on time. It is basically a fixed value. Whereas in the case of a liquid, that theta is time dependent. It continuously basically changes. Theta is not a fixed value. As long as you are applying the shear force or shear stress, there will be deformation, a continuous deformation. That is what the definition of the fluid itself. Because of that continuous deformation, that theta is dependent on time. That is the major change from there to solid to here. So because of that continuous deformation, I cannot write tau is proportional to angular deformation. So that is why we are writing tau is proportional to rate of angular deformation. That time factor comes into picture in fluids, whereas that time factor is not there at all in case of solids. So that you remember. So that is why our derivation, a new dimension for Hooke's law there is equal, tau is equal to g theta, which we call it as some Hooke's law there. But here the Newton's law of viscosity is related to, it is with respect to time, and that is equivalent to the velocity gradient, because it is nothing but the change of velocity with respect to the distance between the plates. How the velocity changes over a change in distance between the plates, that is what dou theta by dou v by dou y. So finally, for Newton's law of viscosity states that tau is proportional to dou v by dou y or dv by dy, and tau is equal to mu into dv by dy. And in problems, actually we use simple relation, tau is equal to mu into v by y. Why tau is equal to mu into v by y is, if you take basically the same phenomena logically, we get similar triangles, and always dv by dy is over a very short distance, but a distance over a distance of some notable distance, quantifiable distance, it will be mu into v by y. So this is the equation or expression that we will use in solving the problems. So we will go into the topic, the next topic, how really the Newton's law of viscosity can be derived and how it can be expressed. So derivation of Newton's law of viscosity. Already I have mentioned to you what is Newton's law of viscosity. Tau is equal to mu into dv by dy, or tau is equal to mu into v by y. How to really do that? So what you do is consider two large plates, because the plates should be very long, kept at a very low distance. My meaning is, suppose this is one plate, this is another plate. So there are two plates which are separated by a very short distance. So this plate, bottom plate, is fixed, whereas the space between these two plates is filled with an oil of viscosity some mu. The space is filled with an oil of viscosity. The distance between the two plates is y. Now this plate is dragged with a force F. Because of that, the upper plate moves with a velocity v. If I take the velocity distribution, this is how it is going to be. So this is v. Here the velocity is 0, and the velocity changes from 0 to velocity here. And this top one plate is the moving plate, and bottom plate is fixed plate, and the space is filled with fluid viscosity mu. So this is the thing. So what are the observations? The observations are like this. First one, the observation is the force is proportional to velocity. That means the larger the force you use it, the greater the velocity with which this move. That anyone you are all can understand. With more force we are dragging, with more actually velocity it moves. The second observation is this force is proportional to basically proportional to next one is the area of the plate, area of moving plate, because you know that shear stress tau is equal to force by area. Stress multiplied by area will give you force. That means more the surface area, more the force. So here, as we are dealing with the movement is horizontal, this force is nothing but the shear force, right? And this surface area is also, remember always, this is surface area. Right? Third observation is the force is inversely proportional to the distance between the two plates. As the distance is very close, naturally more force is required to drag the plate, because already this is a fixed plate. So here the velocity is zero. If you keep it very close to it, automatically what is happening is you if the distance is very small, the force required is more. If suppose the distance is increasing, the more and more distance is there, then it is very easy to pull the plate. Then less force is required for pulling the plate. If you combine all these things, the result is F is proportional to A V by Y. And actually, this is being confirmed also by experiments. Confirmed by experiments. So this F by A is proportional to V by Y. What is F by A? F by A is nothing but stress. This is shear stress. So therefore, tau is a proportional to V by Y, or tau is equal to mu into V by Y. So here mu is nothing but like a constant of proportionality, or in general differential form if we write tau is equal to mu into dV by dy. This is general differential form. If you want how you write that also you want. For example, I take this is the fixed plate and this is the moving plate. Suppose if I take the velocity is v here and this distance is y, this is all filled with fluid of viscosity mu. Now if I take two layers, right, at a distance y, small y from the plate, right? It here the distance is small v, the velocity is small v. In a small distance dy, the velocity change will be dv plus v, right? If I take here this triangle, right? There are two triangles, one bigger one, one smaller one. So this is, if I write this is A, B, C, and this is D, E, F. If you see, so this is how ABC looks like and how DEF looks like. This is DEF. Both are similar triangles only. This angle remains same here or here. Therefore, what you can, but this is what? This is dy, this is dv, this is y, this is v. How you can write it? V tan theta is equal to v by y or is equal to dv by dy. This is what actually we can write, and that is what I represented here. So that is what you need to understand that action. So this completes to me the next equation. What is Newton's law of viscosity and Newton's law of viscosity derivation. So the next most important thing is this mu is called viscosity, or more precisely, we call it as dynamic viscosity. It is called as dynamic viscosity. So, what are the units of viscosity? What are the units of viscosity? What are the units of viscosity if I see it? So, now let us take it. Tau is equal to mu into V by Y. So, what is tau? Tau is shear stress. What is shear stress is equal to force by area. Force by area means force divided by area means L square. I can write like that. Then what is velocity? Basically, V is equal to LT minus 1. It is nothing but meters per second. That is what it is. Then if I take y is nothing but the distance between the two plates. So it is represented by L, right? So now if I see it, let us substitute tau is equal to F by L square is equal to mu into V is LT minus 1 divided by L. So that means F by L square is equal to mu into T minus 1, or mu is equal to, right? Mu is equal to what will happen if I see it? F by the mu is equal to this t will come F by L square into t minus 1. So, or otherwise it will be mu is equal to F into t by L square. What is the unit of F? You know it. It is Newton's. Force unit is Newton. Time unit is second. L unit is length unit is meter. So, what are the units of dynamic viscosity? Units of mu is Newton second per meter square. This is very one, you should remember this. Once this is there, is it common that we write really the, we always express actually how in the normally in the general practice, how mu is expressed? Nobody straight away will write in Newton second per meter square. This is our SI unit, but mu is practically given as poise. Poise. Poise is nothing but it is the name of scientist. Scientist name is Poisely. In his name, we have kept the unit of viscosity is poise, right? But if you somebody gives you in terms of poise, how to, because you cannot directly do any problem in SI system, because in SI system our unit is Newton second per meter square. How to convert this poise into Newton second per meter square? 1 Newton second per meter square is equal to 10 poise. This is the conversion factor. You should, if any problem, if they give it in terms of poise, immediately you can convert immediately into Newton second. 1 poise is equal to 10 to the power of minus 1 Newton second per meter square. Here, one important thing is what is water viscosity? Water viscosity is 1 centipoise. 1 centipoise means 1 into 10 to the power of minus 2 poise, which is equal to 1 into 10 to the power of minus 3 Newton second per meter square. So this is another thing. And last thing here, one point I should make you clear. In fluid mechanics, there is one more viscosity which we will commonly use. Another viscosity which is of use in fluid mechanics. What is that another viscosity is kinematic viscosity. Kinematic viscosity. This is also a common thing, and this will be represented by nu, N-U-E, right? This nu is equal to mu by mass density. This you should remember. The relation between kinematic viscosity and dynamic viscosity is nu is equal to mu by rho, right? Then what is the unit of kinematic viscosity? Unit of kinematic viscosity. Just now we have derived mu is equal to Newton second per meter square, and rho is equal to kg per meter cube. You know it. But if you see, when I divide nu is equal to Newton second per meter square divided by kg per meter cube, naturally how we get the result? No way. So that is why this Newton also should be converted to mass unit. So how to do it? Newton represents what? Actually, it is force. What is force is equal to mass into acceleration. So what is the unit of mass? It is kg. What is the unit of acceleration? It is LT minus 2 meters per second square. Right? Kg into meters per second square. This is that you can replace newtons with this. So if you do it that same way, therefore nu is equal to kg meter per second square into second per meter square divided by kg per meter, basically cube, sorry, kg per meter cube. This finally represents to you, it represents to you meter square per second. Simplify it, very simple. So nu unit is meter square per second, right? Then what is the general unit, practical unit, general or practical unit of the practical unit of nu? The practical unit of nu is Stoke. So nu is expressed in terms of Stoke. Again, Stoke is another scientist related to fluid mechanics. So therefore, but now we cannot use Stoke in a problem. Then how to convert Stoke into our unit meter square per second? So the conversion factor from Stoke to way to meter square per second is 1 Stoke is equal to 10 to the power of minus 4 meter square per second. Very, very, very important, because these type of things are important for you to solve any problem. So what is first nu I mentioned? What is first mu I mentioned? Actually, there are two viscosities for you. One is mu. Mu is a dynamic viscosity, and dynamic viscosity is expressed in Newton second per meter square. And what is the general unit? Poise. And what is the conversion factor? 1 Newton second per meter square is equal Newton second per meter square is equal to 10 poise, or 1 poise is equal to 10 to the power of minus 1 Newton second per meter square. This is very, very important. Otherwise, you cannot solve problems. Please note it. Nu is kinematic viscosity. And what is the relation? The units are meter square per second. What is the relation? Nu is equal to mu by rho. And what is the unit of it? Stokes. And what is the conversion factor? 1 Stoke is equal to 10 to the power of minus 4 meter square per second. So here I stop.
like, share, and subscribe. Hit the bell icon for more updates.